Okay, hope you are back. We'll begin. The next topic that we are going to look at is the case of don't cares. Don't care conditions. In certain applications, when you try to design a digital circuit, let's say there is a case of 4 variable inputs. Okay, A, B, C, D. So these are the input boolean variables, and in such an if you look at an application where, for example, we are using these 4 variables to represent a decimal digit. Okay, we know that a decimal digit is from 0. So we are looking at a particular application. Consider application of inputting a decimal digit. Okay, the input is basically a decimal digit, and we will use the 4-bit binary code to represent the decimal digit. Okay, just like we have seen earlier, BCD, binary coded decimal. So we will use a 4-bit code to represent the decimal digit. So decimal digits are basically 0, 1, 2, etc. up to 9. Now you will never have a case anything above 9, because we don't have a simple decimal digit above 9, right? We have from 0 to 9. This is a single digit that we have, only 10 combinations. But if you use a 4-bit code, there are many more possibilities which are possible, which are not included. So when you say 0, you give 0, 0, 0, 0. When you say 2, you give 0, 0, 1, 0. When you say 9, you give 1, 0, 0, 1. So until then we have clarity, but we are never using these 6 combinations anytime, because there is no decimal digit which can be given as input that will use those code. So such conditions are called don't care conditions. Okay, so in such an application, so here the codes or the binary input, why it is here, binary inputs, say 1 0 1 0 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1, never arise as an input. So this case doesn't arise. You never give an input combination which is either of the 6 combination. So in such cases we treat, therefore we treat those as don't care, because they never arise in our system input. As a system input, they never arise. Okay, these combination, but all other combination arise depending upon whatever decimal digit you are specifying, they will come, but these combination never arises. Okay, so if you have a function of these if you have a digital system which is given, which is taking this ABCD input, 4-bit input, and then giving you a boolean function. So therefore f of a, b, c, d. A very good example of such a function is basically 7-segment LED. So 7-segment LED, probably you must be aware of. You must have seen it in railway station. They display these numbers like this. They are arranged like this. There are 7 segments like this. So depending upon which segments are lighted up, you will see different digits. Okay, but these are the 7 segments and they are numbered as basically A, B, C, D, E, F, G. The 7 segments are numbered like this: A, B, C, D, E, F, G. Okay, so this is E. Now so when you want to display any of the decimal digit, you give input from 0000 to 1001, and depending upon the digit we need to lit up a chosen number of segments in order to display that digit. Okay, so we give a binary input and then we display a decimal digit by lighting up the corresponding combination of the segment, and some segments will remain. For example, if you want to display 0, what will you give? You give 0 as the input. So if I write a truth table of a 7 segment, so that is a good problem to solve. So let's draw the truth table. So we have A, B, C, D, and they are going to take, so there are 7 segments, so you have A, B, C, D, E, F, G. Okay, so each you can treat like a light. Basically they are LEDs. Under each segment there is an LED. So depending upon whether you give 1 or 0, the LED will either light up or they will be in off condition. So let's say that we have an LED which would light up if you give a 1. Okay, such kind of LED display, 7-segment display, is called common cathode. Okay, so we have different LEDs. So let me just denote here. So this is, say, this is one LED. I am not arranging them in the shape of 8 like before, but just showing it. So this is our A LED, this is B, C, like that. Many LEDs are there, 7 of them. This one is G. Okay, and they will have a common cathode. It means all the N side of the LED get shorted together and connected to the ground, and there will be some current controlling resistor like this to each LED, and here we give inputs. Okay, either high voltage or low voltage. If you give high voltage to A input, this A will lit up. Okay, LED means you have this symbol also. Okay, there is 2 arrows to show it is not just a diode, it is an LED. Okay, so if you give a high voltage, it will lit up. If you give a low voltage corresponding to 0, it will be off condition. So if you want to lit up a common cathode LED array, you just need to give 1 wherever logic level 1. Okay, that means high voltage to whichever LED you want to lit up. For example, let us look at the case of 0. So when it is 0, to get a 0, what we need is basically lit up all these LEDs. Okay, the last LED, that is G, should not be lit up. So G should be 0, G should be 0, and all other should be 1. Okay, so that will lit up A, B, C, D up to F, but G is given as 0 input. Okay, so high voltage is given here, high, and last one is given low voltage because it is 0. Logic 0 means low voltage. We are using positive logic. Okay, and so all the segments except G segment is going to be lit up, and we get a 0 displayed like this. So when the light is glowing, this LED will show like this, brightened color. Usually we see red color, so depending upon the type of material with which you build the LED, you can have different colors also. Okay, so the middle segment is not lit up, so that is done by giving a 0 there. All other we give 1 or high voltage.
Which means, sir?
Yes.
Sir, shouldn't there be a function, sir, for that 4 inputs?
No, these are the inputs. A, B, C, D are the input. And
Sir, we have given
output
a
of
4
the
input.
so we have actually a digital circuit to which we give input, which will give an output. Output of the digital circuit is connected to the LEDs. Okay,
Yes, sir.
is that clear? Okay, you can think about like this. So you have a, say here there is a digital system. Okay, this is a digital system that we are designing, so to which we give inputs, 4 inputs, A, B, C, D, the code corresponding to 0, code corresponding to 1, 2, 3 up to 9 we will give. There will not arise any other combination here because there are only 9 digits, right? And we have 7 output for this digital system, which is actually each one is going to one LED, like here I have done A, B, C, D. One goes to A, another B, another C, etc. up to G. Clear? These are the
Yes, sir.
voltages which are going into the LEDs.
Sir,
Yeah.
sir, that corresponding to 4 inputs, sir, 0, 0, 0.
Ah.
This A, B, C, D, E, F, sir, it is turning as 1.
No,
Sir,
no,
are
you
we
are talking
following?
about big A, capital A, B, C, D, or small A, B, C, D?
Sir, small A, B, C, D is turning
Small A, B, C, D,
into
if you
1,
want to
sir.
display 0, this one is 0, right? To display 0, you see here, I have written a 0 here. I illuminate A, B, C, D, E, F. This is A, B, C, D, E, F. I illuminate all this, but G I don't illuminate, the middle one. That LED will be off. How we can do
Yes.
that? We give 1 to each of this LED from small a to small f. And G, here this input, we give a low voltage or 0. Logic 0 means low voltage, logic 5 means logic 1 means high voltage. So that output is generated by the digital system, which we need to give to the LEDs.
Sir, then these outputs are being controlled by the digital system.
Yes. So that is
ABC,
so
small ABC.
there is a circuit inside this which we need to design. That is a problem.
Okay, sir.
Yeah.
Yeah.
Okay. Very good. So now let's look at. So if you look at a different combination, this will become more and more clear. So 0, 0, 0, 1. So can you tell me which one we need to illuminate so that we will get a figure of 1?
BC.
BC, correct. Usually we do BC illuminated, all other off. Okay, so 0, 0, 1, 0. This is a practical problem. Okay, so far we did some random functions, but now we see that we get a practical problem, and out of the practical problem we have a digital boolean function coming out. Okay, next one, 1, 0.
Sir, A, B, G, E, D.
A, B, G, E, D, correct. All other will be 0. Next, 0, 0, 1, 1. 3. F and E. F should be 0 and E should be 0, right? All other should be 1. Then 0, 1, 0, 0.
F, G, C. Should be 1.
So A and E, we can keep 0, right?
Yes, sir.
All other 1. Okay.
Sir, A, E, and D also should be 0.
No, we want a figure of 4, right?
4, yes, sir.
So figure of 4, if you look at, this is figure of 4, right?
Yes, sir.
Oh, okay, you are right. You are saying D should also be 0, right?
Yes, sir.
Yes, correct. D should also be 0. So 3 things should be 0. D, E, and A. Yes, A, D, E. Next one, 0, 1, 0, 1. This is 5. So A, B is not there. C, D, E, F, G. So A should be 1, C should be 1, D should be 1, F should be 1, and G should be 1. B and E should be 0. Okay, next, 0, 1, 1, 0. Uh, 5 itself you take and then add E also, right? Add E also, leave only B. That will give you 6. Now depending upon whether you want A or not, that's an option. You can write 6 this way also. You can write 6 this way also. So which looks better, that you decide. Maybe this is better. This look a little bit like B. I think this is better.
The second one.
Yeah, second one is better. Okay, so now let's look at 7. 0, 1, 1, 1. Okay. What is it? 0, 1, 1. This one. So 1, A, B, C. That's all. Okay. A, B, C. Everything else is 0. 8. 8 is easy, right? Everybody should say 8 quickly. All one. We need to lit up everything. 9.
D and E
Except
0.
E, right? Except E, everything should be except
So
E.
D also.
D also. No, so that's a choice basically. You are talking like this. I am saying like this, which is better.
Oh, yes. Okay, sir.
Yeah. So
That looks better.
Yeah, that looks better. So let us just uh, exclude E and all else. Right. So that's it. These are the only possible input that can come to the circuit. The reason why I chose this problem here is so that this is a practical case of don't care condition. Now the input in principle can take more combinations, but for this application that never arises. We can never give an input other than the digit that we want to specify. So there will be like you may have a keypad with 1, 0, 1, 2, 3 up to 9 written. So there is no other combination you can give as input. So whenever you press the key corresponding to 0, the code corresponding to 0 will go. Whenever you press the key corresponding to 5, the code corresponding to 5 will go 0, 1, 0, 1. And since there is no key to press other than these listed combinations, no other code will go. So in this example it is like this. So in such cases, how do we find the simplified expression? Okay, since those cases, the remaining cases doesn't arise, what we do is that we write down those cases like 0, 0. Okay, this is 1, right? This is 1, 0, 0, 1, 0. We write like this, don't care. Could be 0 or 1, we don't care. That's basically the idea. And same thing we continue up to 1, 1, 1. We don't care. All these cases, we don't care what it is, because we are not going to give these inputs. So the corresponding, either we can assign 0 or you can assign 1, we don't care. Okay, so now you see how many boolean functions we got. We got 7 boolean functions. For each output of that digital system, we have got one boolean function. So A is a boolean function, small a is a function of capital A, B, C, D. Small b is a function of capital A, B, C, D. Small c is also a function of capital A, B, C, D. So we got 7 boolean functions. So now we need to solve 7 k-maps. So now our query is what is this function in the simplified form, so that we can implement, and what is this function, okay, etc. up to G. Okay, so I will solve only one. Rest I am going to give you as a homework. You can find out it in the similar way. Any one I will take and solve. So that will be an example of Boolean function with the don't care. So if I try to find the expression for A, okay, or let me just write down the minterm representation. Sigma 0 is there, 1 is not there. So this is for A, okay. A is basically, so 1, then 0, then 1. So 2 is there, then 3 is there, 4 is not there, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9. This much minterms are present. And the rest we say plus. Don't care. Don't care is basically 10, 11, 12, 13, 14, 15. This is how we write the relation. So 0, 2, 3, 5, 6, 7, 8, 9. Okay. Sigma 0, 2, 3, 5, 6, 7, 8, 9. Then plus don't cares 10, 11, 12, 13, 14, 15. Now we can enter things, we can go to the K-map method. So what do you do? Draw the 16 squares, because there are 4 variables. We need 16 squares. Then denote 2 inputs here and 2 input here. Write the combinations possible in a 1 literal change order. Right? Then enter the ones. So 0 is there, 2 is there, 3 is there, 5 is there, 6 is there, 7 is there, 8 is there, 9 is there. So this many ones are there, sigma. These are the minterms. Now then we have don't care terms. So minterms and don't care terms. So minterms are those ones, right? So let me just denote. So this is minterms, and these are don't care. How do you enter don't care terms? We put X. So don't care term. Which are the don't care? 10, 1, 0, 1, 0. 11, 12, 13, 14, 15. These are the don't care. And the remaining empty ones are zeros. There are 2 zeros. Okay, so if you go back again, look at this. There are 2 zeros. They correspond to 1 and 3. Sorry, 1 and 4. Okay, so this is 1 and this is 4. Alright, now comes the grouping. Always try to make bigger group. That is our policy. Always try to cover. So you have to, whenever you try to group, you have to cover all the ones. No one should be left behind. Okay, so that is one principle that you have to follow. And secondly, make each group as big as possible so that we get larger simplification, lesser literal in the product term. Now, which are the essentials? Look at for the bigger group possible is basically a group of 8 is possible. If only take one, only group of 4 is possible, for example here. But these don't cares, we can treat them as 1 or we can treat them as 0. So we will take an advantage of the don't care condition by treating them as 1 if we can make a bigger group. So if a bigger group is possible to be made, then we will treat those don't care conditions which are adjacent to those number of ones in order to get a bigger group. So for example, the 2 ways I can make group of 8. One is like this, other is like this. These are 2 possibilities. Now Does both of this are essential? What do you think? Are they both essential? Essential prime implicants, the term that we get.
Sir, your writings are not visible, sir.
You are not seeing my screen?
Sir, yes, sir, it is visible, but your writing is not visible. So did you just write something?
Let me do one thing. I'll just present it again. Now is it clear?
Yes, sir.
Okay. Now my question is, there are two ways you can make a group of 8. Okay, let me just show you that. One of them is basically doing a group of 8 like this. Another is making a group of 8. These are the two possible ways I can make group of 8. The question is that are they both essential? Based on what you have learned about essential prime implicants, can you tell me whether those terms that will arise out of these groups, are they both essential? Are you getting my question? Hello? I am asking, in order to get the simplified expression systematically, we are using K-map. And in the K-map, we have said that we can use don't care condition in order to get a bigger simplification, to get bigger groups. If you do so, there are two ways you can get a group of 8. This is only two possibilities. I have shown it here. One is this horizontally, other is vertically like this. Question is, does they both correspond to essential prime implicant or not? Does both of them correspond to essential prime implicant? Can you respond?
Maybe yes, sir.
Yes. Yes, right? Because, for example, these ones cannot be covered with this group of 8. Right? For that you need this group of 8 itself. So, similar sized group is not possible to cover these ones as well as these ones. So, you need both of them. So, now let us group these 8. So, this is an essential prime implicant and this is another essential prime implicant. Now, let us write the terms. So this is basically A of A, B, C, D. Now what is this group? This is capital A, right? This is A. What about this group? This is C. Okay, there is only one literal because it's a group of 8. All the other 3 literals got simplified. Now, but we have not still covered these ones. So can you make it part of the group of 8? No. Can you make it part of group of 4? What do you think? You are not responding. You can make a part of group of 4, right? And what is this group? Tell me, what is this group of 4? Look at A is changing, B bar. Then there is a 1 0 here. C is changing, D is 0. B bar, D bar. So we can write B bar, D bar. Still there is one left. There is another one left. So now the green group, is it essential? Can you make it part of any other group of 4?
Also.
No. So that is also essential. All these three are essential. If two people are doing, all of should get these terms. Okay, there is still one more one left here, which is not covered, and we cannot make them part of group of 8, but we can definitely make them part of group of 4. And can we do it in multiple ways, or is it only one way we can do it? To cover this one, by making them part of group of 4, can we do it in multiple ways, or is it only one way we can do it?
Excuse me, sir.
Yes.
Sir, can you please repeat your question, sir? I'm not getting your
Okay,
question.
I am highlighting. So there is a one here which is not part of any group. We have made so far 3 groups. First one is A, and the second one is C. Here this one is C, and the third one is the green group, which is B bar, D bar. And after doing this 3 essential group, we have still one more one left. The question is, how can we make a group to cover that one, and is that group essential?
Yes, sir.
So which is that
Group of 2, sir.
No, group of 4 is possible, right? Here,
Oh, yes, sir. Including
don't care.
don't cares. Yes, sir.
That is the purpose of this example. You
Yes, sir.
have to know what is don't care condition. So I can make a group of okay. Now what is this? Expression? Can you tell me the expression? What is the expression?
Sir, B,
Sir, BD.
B,
B
yes,
and D.
and D. Yes, sir.
Correct. That's it. Now all these terms are essential terms. They are essential prime implicants. Okay, why? Because there is no other way you can cover this one other than this BD. There is no other way you can make a group of 4. Of course you can make a group of 2, as you said, this way or this way, but whenever you consider prime implicant, you have to make it part of the bigger group. Then see whether any other similar sized group you can make it part of. If not, then it is an essential prime implicant. So prime implicant will have the biggest group possible to cover that particular element, and if that is the only biggest group that can cover that one, then it is an essential prime implicant. So the function finally what we get is A plus C plus B bar D bar plus BD. And this is XNOR operation. Okay, is it clear? How do we get the boolean function in the standard form? This is standard SOP form. Now same thing you can do with the standard POS form also. Then
Excuse me, sir.
Yes.
So is it not possible to group them into 3, sir?
No. See, why do we insist on grouping them into 2, 4, 8? because they correspond to the simplification. You look at for example, we get A. What does that mean? A means A into B plus B bar into C plus C bar into D plus D bar. This is what we are saying. This is 1, this is again 1, this is again 1. So if you expand, how many terms will you get?
One single, sir.
How many product term you will get if you distribute and expand?
Oh.
This is just an algebra, right?
Sir, by distributive property, sir.
Yes.
Okay. Sir, A dot B.
I mean, if you write all of this, it will take a long space. But can
Yes,
you just
sir.
tell me by looking how many terms you will get? There are 2 terms here in the bracket. There are 2 terms here in the bracket. There are 2 terms here multiplying. Is that difficult to say? Each element is distinct, right? So there will be no cancellation. Okay, so if you are not convinced, you can expand it. So first you distribute, so you will get AB plus AB bar, right? Then again you distribute, so ABC plus ABC bar plus AB bar C plus A B bar C bar. Again distribute, how many terms did we get?
8, sir.
8, right? So 8, these 8 terms can be simplified and shown it as A. Okay.
Yes, sir. Yes, sir. Yes, sir.
Similarly, if you take BD, this is another term here which we got, BD. I can take BD and multiply it with A plus A bar and C plus C bar. How many terms I will get? Hmm? Earlier when
Sir, here 3 terms. 3 terms.
will you get 3 terms? See, it's very easy to see. This A will go here, A will be combined this.
So will it be 6?
How many terms?
3, 4, 5, 6.
1, 2, 3, 4. There are 2 possibilities here, 2 possibilities here, 2 into 2, 4. Here it was 2 into 2 into 2, 8.
4.
4. So there are 4 terms. So these 4 terms you can simplify and show it as BD. Here these are 8 terms. 8 terms you can simplify and show it as A. So that is how it comes. This 4, 8, and similarly you can say if there is a term called ABC, you can multiply it with D plus D bar and you will get 2 terms. So these are the only possibilities that will arise after simplification. Okay, either group of 8 means you are simplifying by reducing 3 literals. Group of 4 terms means you are reducing by 2 literals. Group of 2 means you are reducing it by 1 literal.
Yes, sir.
Okay. So I hope that confusion is gone now. So whenever we make a group of 8, if you look at all the terms which we have listed, that they are actually part of this group. So by grouping them, we are essentially combining these different terms. For example, you can first combine these 2 terms. So D plus D bar will go away and it will become ABC. Again, same thing here, same thing here, same thing here. You can combine all of this. So you will have ABC here, ABC bar here, AB bar C here, etc. And then ABC and ABC bar you combine, you will get AB here, and here you will get AB bar here. Then again you combine and you will get A. So boolean algebra you can do using the postulate and theorems, but systematic way is to use a K-map and get the simplification. This is very, very basic. Everyone should understand this topic, how to simplify the given boolean expression. So given boolean expression, we have it in this form, minterms and don't cares. So they can be simplified and get the most simplest expression. Everybody will get this expression if you do it, because all of the terms are essential prime implicants. If some of the terms are not essential prime implicants, there can be difference in the answers, but not in this case. The function small a, which is one of the 7 output of the digital system that we are designing, one of the 7 output. So that will have a same answer for everyone. Now in the next digital lab, you can implement this. So you should give a code 00, then 0 should lit up. You can start working on it. You only need to find out the boolean function and then implement the boolean function using the logic gates and verify whether you are getting what you require. Okay, since you are familiarized with the software, you can find out the other boolean functions. Okay, so this is only for A I have done. B, C, D up to G you do it. Okay, same way you draw the K-map. So 7 K-map you have to draw. 1 is already done, so the remaining 6 K-maps you have to do. Get the grouping done and write down the function like this.
Yes, sir.
Yeah. So that will be a good exercise for you to learn K-map as well as working with Logisim. So, okay, so now we have some 10 minutes left. So let us look at what is called as 5 variable K-map. So far we did only 4 variable. Now can we do 5 variable? And if at all we have to do 5 variable, how do we write it? Okay, so let us there are 2 ways in which you can solve 5 variable functions. So again, the function may be given as before by specifying the minterms, etc. and don't cares also can be specified. Okay, so let me try to take an example from the book itself. Okay, somehow that not getting an example. Okay, we will create an example. Okay, so what I will do is, I will first of all tell you how to five variable came up. So first method is draw two 4 variable came up. 4 variable came up, everybody knows by now. You draw two 4 variable came up. Okay, so let's say the inputs are A, B, C, D, E. Now you eliminate your A here, the first one, reserve it. B, C, D, E you put here. Then you proceed as before. Okay, and you say here this is for A equal to 0. This 4 variable came up is for A equal to 0. Then on the right side you draw another. Ideally it should be 3-dimensional, but that is difficult to draw. So you have to imagine. So this is for A equal to 1. Again B, C, D, E. Okay. Now let us, since I have not, I couldn't find a question with 5 variables, so I am going to put ones, and then I am going to teach you. So I am going to put 1 here, 1 here, 1 here, and 1 here, 1 here, then 1 here, 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. Okay, let's say that these are the cases. Now we need to first of all identify each column. Since A is 0, I can immediately say that this is M0, M1, M2, sorry, this is M3. Always be careful. Then M4, I'll just denote 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Then comes 16, 16, 17, 18, 19, 20, 21, 22, 23. Then 24, 25, 26, 27, 28, 29, 30, 31. Are you able to understand what I did?
Yes, sir.
Okay, very good. So when A equal to 1, that we have reserved the first bit, MSB bit, which is the most significant bit. So that 1 means this will be the last 16 and this is the first 16. Okay. A equal to 0 for first 16, A equal to 1 for the next 16. And the order in which we proceed, it is the same in both. Okay, 0, 1, 2, 3, here 16, 17, 18. 18 is here, 19 is here. Okay, so that is what you need to keep in mind. And then the next row, then the fourth row, then third row. So whenever we go in a row, first column, second column, fourth column, third column. Whenever we go in row also, first row, second row, fourth row, then third row. So that is how you do. So I have already given the function. So what is this function? If I write it in minterm representation, the function a comma b comma c comma d comma e can be written as sigma. Can you tell me? Three is there, then 7 is there, 8 is there, 9 is there, 10 is there, 11 is there, 15 is there, then 19, 23, 24, 25, 27, 31. So these are the minterms. Wherever I put the 1, I denote that number. So this way you can, so question may be given something like this. Okay, and if there are don't care condition, that will also be specified, plus don't cares. So let me put some don't cares also. So don't cares I'll put here, here, here. Just randomly I am putting here, here. Okay, so these are the don't cares. So what are they? 2, 6, 14, then 26, 30. These are the don't cares. Now the question is, what is the simplified expression? All the data is given. We have put them in the K-map, and then now we need to group and write the expression. So you need to know the nearest neighbors here. Apart from the nearest neighbors which we specified for the 4 variable K-map, we have additional nearest neighbors, and that is basically this cell or this particular in the corner and this one in the same position. They are nearest neighbors, because the only difference is A is 0 here, A is 1 here. One variable change. B, C, D, E are same, right? 1, 0, 0, 0. But A is 1 here, A is 0. So you need to know that. So you can keep imagine that one is on the top of the other. One 4 variable K-map is on the top of the other 4 variable K-map. So you can visualize the nearest neighbors. So each cell has a corresponding cell above. Okay. So whenever you group, you have to group by keeping that in mind. So what is the biggest group you can make? What is the biggest group you can make? Okay, combined. This is the biggest group. A is changing, then D is changing, E is changing. Only B and C doesn't change. So therefore this corresponds to a term B C bar. Okay, I have included this don't care. Again, we need to cover the remaining ones. It is not necessary that we should cover all the don't cares. That is not our point. Don't cares will be utilized only to minimize, but we are not it is not necessary to cover them. Okay, the next group is and they are on the top of each other, so they are part of one group of 8. So this is a group of 8, not a group of 4. 4 here, 4 here, they are combined. And what is this group? A is changing, B is changing, C is changing, only D and E that is not changing. That's it. Few don't cares are left, but we don't care. If don't cares are left, we don't care. But if there is any one left, we need to take care. So therefore, this expression is very simple. It is basically B C bar plus D E. If this don't care was not there, then we would have got a more complicated expression. Okay, because you couldn't group this green group like this if the don't care was not there. So in that case, we need to make two groups of 4 and each group of 4 will have 3 literals, and there will be 2 such terms will come. Okay, I will write that also without taking into don't care into account. The second group will remain, DE will remain, and the third group that we will have, one is like this 2 and this 2. Right? Okay, so and that will give you basically B C bar, B C bar, and one more variable will come, that is D bar. So that will cover these 2 and this 2. Now I need to cover this one and this one. So that will give you B C bar and E. But still there is one that is left to be covered, so we need to cover, and there is nothing. Okay, we can group them into group of 2 like this, or wait a minute, we can group them as a group of 4 like this, as another group of 4. So that will be A0, then B C. Okay, so this would have been the term that we would have got if the don't care was not there. So we just utilized one don't care, we got a huge simplification. Instead of this last 3 terms, we got basically B C bar. Okay, so this I will specify that this is without exploiting the don't care condition. So don't care is a very good thing that we can take advantage. That is because such cases never arise in our system. Okay, and under that assumption, we are treating them as ones wherever we want to make bigger group, just to make a higher level of simplification. Okay, so this is with the don't care. This is with the don't care. So this is the correct. For this problem, this is the correct method. But I am just showing it just to show you the power of don't care if we include them. Now, any questions? We will stop here. If there is any question, you can ask. Otherwise, we will meet tomorrow.
Hello, sir. Sir, can you explain about the prime implication, sir? Sir, actually, I joined the class little late, sir. Just a brief explanation, sir, if you can give.
Yeah, okay. So, did you were present in this, no? This problem? When we found the function for A?
Sir, I just saw the function that you wrote, sir.
So, the first hour you were not present?
No, sir.
Oh.
Actually, sir, I was 5 minutes late, sir.
Now if you are only 5 minutes late for the first hour, you should have seen this problem, no? The LED 7 segment display.
Sir, yes, sir, I have seen that. And
Okay.
sir, the
So
beginning lecture, sir.
I mean, same concept is here only. But if you want the earlier problem, I can take that also.
Okay.
Yeah, this is a problem from the book. You have a function given like this, and then you enter the ones, that is the minterm which are present, you enter it, and then you try to group it. Now there are so many ways in which you can group this function. Okay, there are so many ways you can group, out of which two of them are essential, which I denote it with green group. Okay, the green color is representing the essential groups. Okay, why do we say that this group is essential? Because I have highlighted a 1 here and a 1 here. If you look at the group made of the corner elements, that is the biggest group that can include this 1, the one at 0 0 0 0. Are you getting?
Yes, sir.
Yeah, but can you find any other group of 4 which can include this 1 which is highlighted at the corner? Can you find any other group of 4 which can include that one?
No, sir.
No. Therefore we call it as essential prime implicant. Okay, if we cannot find any other similar size group which can include that one, that particular group only is the possibility, and we call it essential prime implicant. So when you simplify a boolean expression, those term, those prime implicant will definitely be present. If two people are solving this problem, both of them will have those terms present in their expression. Now if you similarly, there is another one here, another one which I have highlighted, which is here corresponding to 0 1 0 1. That also there is only one group which can cover it, one group of 4. But if you look at any other ones, there are many more ones here. You take any other ones, you can show that it can be covered in multiple ways. For example, this corner one, the top corner, 0 0 1 0. This group can be, this one can be covered by the green group, or it can be covered by the purple group. Multiple ways. Both are group of 4. Similarly, if you consider this corner, the last corner, it can be covered by the green, it can be covered by the yellow or orange, it can be covered by the purple also. Multiple choices are there. So you take all other cases, those ones can be covered by different ways. So they are not really essential. If one is not there, other can take care. So when you solve problems, some students may get the option 1 as the answer, option 2 as the answer, or 3 as the answer, 4 as the answer. But the first two terms, which are essential, will be common to all the answers. But the last two terms can differ, because they are not essential prime implicants. Prime implicants, all of these are prime implicants, but two of them are only essential. Okay, is that clear?
Yes, sir.
Okay. Any other doubts? So I want all of you to go along with me and continue this journey. You should not, leave behind. Okay, so you try to catch up. So right now we are doing only one subject, but next week onwards I will start all the subject. Okay, so this subject I have taken so that the diploma students already are familiar with